Okay, good. So welcome back. Last time we started the proof of Riemann mapping theorem, one of the most important results from this course. And today we will complete it. So it won't take much time. So today we may end a bit earlier than usual. Let's see. Or I may go slow enough. Let's see. So let me start sharing the screen. So before going to today's slides, I thought I'll just show you this. You can see my desktop, no?
Yes.
So, maybe on September 9th, I did make a remark that lecture 9 came on September 9th. Yeah, and yesterday night only I noticed when I took the previous file to create the new page, a new Beamer file, that once again lecture 16 came on the 16th, October 16th. So this I did not notice that day, noticed it yesterday night. I don't know what the point of saying all this is, but I get some pleasure by noticing these small things. So this happened because I cancelled one lecture, right? I had no such idea when I cancelled for some other reason. I was busy with something else. So yesterday night I felt very happy that I cancelled that lecture because these numbers coincided. Anyway, so how do I put this?
Is the colon the difference you had mentioned earlier?
Yes, you noticed it just now,
Yeah.
Ariman?
Yeah.
Because what you now you can guess the reason also.
Because the digits became double.
Because
You went on to double digits.
yes, so I did not know how to adjust the font size here. Plus, I did not want to adjust. I wanted uniformity. And when I started 10 here, the 10 was going downstairs. I mean, the second line was forming. So I thought way to abbreviate. I thought of making this ANAL dot. Then I knew that that's not good. Functions, I thought of writing FNS. Then I thought, I'll just delete the column. Yes. Good observation, Arjun. Yeah. Uh, this reminds me, I also said last in I will have an assignment without marks. There's a result that I stated, and I said I will try your Google searching skills. No, you remember this, Arjun? I
Yeah, I
said,
remember.
yeah. So maybe I will not ask that as an assignment, but do you know the answer?
Yeah.
Okay, maybe you can tell me.
Osgood's theorem.
Yes. And was it easy to find out, or
Yeah, I found it out like within my second search, I knew
very,
what
very,
it was. Yeah.
very good?
I
So
think I found the exact paper also, which had the Sierpinski gasket and all that.
1910 or 1902 or something.
That I don't
It's an
remember.
annals paper, right?
Sorry?
It came in Annals of Mathematics.
Yeah.
Uh, so I don't think I have the paper downloaded here.
For that, I needed the JSTOR thing for
Uh,
IITB.
but that you can access even without IIT now, no?
Yeah, I had to look at the, what do you call it? I had to use the VPN.
You needed
The,
IIT
yeah,
IP or
yeah, I needed that. Yeah.
after Corona they made it free for everybody. JSTOR access. No, that's not true.
No, 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 I don't think that happened.
Maybe for a month or something that happened. I don't know. So, roughly, do you remember uh,
Yeah, no, yeah, I found it. So it
what?
was American Math Monthly.
No, that is the
Uh,
article about Osgood's original paper. Osgood's
the
original.
Osgood's theorem also was in, oh no, sorry, yeah, yeah, yeah. That was in Annals of Mathematics, Volume 3.
Yeah, so I will just search. Yeah.
Yeah.
Okay, yes, many annals papers. So let's see. This was when
This was 1901,
1901.
Volume 3, pages 25 to 34.
This one, right?
Yeah.
not on the functions defined by infinite series whose term, oh, what a title, such a long title, whose terms are analytic functions on a complex variable with corresponding theorems. This is the paper? Yeah, this is the paper, right?
This was the one. Yeah.
Yeah, so I reached there via maybe a paper of Kranz, but not this one, another expository paper of Kranz, Stephen Kranz. Yeah. Do you recall the research? We wanted to say, so we constructed this polynomials converging so that at 0 it is 1 and everywhere else it is 0, etc. And we want to say that that's the only kind of exception that can happen, no?
Yeah.
So what was the result then? Dense, something about dense subset?
Yeah, I think so. Open dense subset.
Remind me the result. What
No, I
did you...
don't remember the exact thing
No,
now.
because I also remember you said a similar result you proved in calculus, real analysis, and it was there in monk race.
Yeah, so that was also that if you have a sequence of continuous functions,
Yeah,
you can't get a nowhere continuous function as a pointwise limit. It'll still be continuous on a dense set, I think.
continuous on a dense set. Okay. So let's just okay, but I might not have stated it in my slides, but we can still go there. So this must have been which lecture? This must have been just before the break,
This
no?
was on 25th September
So that
when
must be 14.
that was lecture 14, yeah.
So let's just see that towards the end I might have, but I think I only stated this verbally. I don't think it was part of the slides.
It
No,
was part of the exercise which you showed us in
but
Doodle.
was it the 14 or 13? 14 is already equicontinuity, Montel and all that. It must have
Yeah,
been before that.
this was 14 only.
No, it must
21.
have been 13 because this was about Montel's theorem. Ah, okay. Runge's theorem exercises. Yeah, okay.
Yeah.
So, okay, since anyway we are talking about it, let's just see it once. I should get it here. Okay, so our class is yet to start. It's at 276. This one like this. So you have a sequence of holomorphic functions. You have a sequence of holomorphic functions on omega, and you are taking the limit, pointwise limit. Then on a, yeah, so yeah, we proved that uniform compact convergence, when it is there, limit will be holomorphic, but pointwise limit it is not true, as this exercise shows. Right? These two exercises show that pointwise limit need not be holomorphic, but you can get it on an open dense subset. So if you have holomorphic functions on omega, and if you take the pointwise limit, then omega has a dense open subset on which f is holomorphic. So going back to this example, here, yeah, on an open dense subset, except at this point 0, everywhere else it is constant function 0. And here open dense subset is you can take C minus 0. C minus the x-axis. The upper half plane together with the lower half plane, there also is holomorphic. Okay. Yeah, so this was just recalling. So Osgood's theorem. Okay, so let's come back to today's lecture, which is 17. And let me make it full screen. Good. So let's start now. Riemann mapping theorem continued. It's visible, no? The slides?
Yeah.
Yeah, okay, good. Let's continue Riemann mapping theorem. So in the last class, we started the proof. In fact, we finished half or a bit more than half. Today, we will complete it. So recall that we have already made use of, so this is one thing that I like stressing, that we are using a lot of, it's always good to see applications of what we have already done. So this result uses a lot of results that we have proved. So we have already made use of existence of holomorphic square root for non-vanishing functions. This is because we are assuming our region is simply connected. And using this, we are going to prove that, so because it is simply connected, we have this, but we are not assuming simple connectedness in the proof anymore. We only assume this particular property, that you have a region on which, if you have a non-vanishing, everywhere non-vanishing function, holomorphic function, it does admit a square root which is also holomorphic. And then we are going to show that it is biholomorphic to the open unit disk, and therefore it is simply connected. Okay, so the statement of the result will be that if you have simply connected, you can establish such a biholomorphic mapping. But what the proof shows is that if you assume this particular property, then you are proving it is biholomorphic to the open unit disk and therefore simply connected. So this would also prove, so what we are proving in these two classes is, one, the Riemann mapping theorem, and another, the one characterization which was left that time in the 9 equivalent characterizations of simply connected domains. So remaining one is also getting proved now. Okay, so keep that in mind. So this we used, and we used it twice. We used it, we made two claims. In the first claim we used it, in the second claim also we used it. We used open mapping theorem once, we will use it once more. And we used what Rudin calls the extremal problem we did after Schwarz's lemma. So what is this extremal problem? If you have a function from u to u, holomorphic, and if f of alpha is beta, then f prime alpha you can bound as 1 minus mod beta square by 1 minus mod alpha square. This we did using Schwarz's lemma. This we used. We also used Schwarz's lemma itself in the last class. And now we are going to use Montel's theorem, compact convergence, meaning this result that we proved long back, that if Fn converges to F compactly, uniformly on compact subsets, and if Fn's are holomorphic, then F is holomorphic. Not just that, Fn prime will converge to F prime, Fn double prime will converge to F double prime, etc. Okay, so that result we are going to use. We are also going to use open mapping theorem once again. And we will also use Rouché's theorem. Okay, all this we are going to use to finish the proof of Riemann mapping theorem. So let's briefly recall, since we stopped in the middle, I will just recall what we did in the last time, a bit more detail, in a bit more detailed fashion, and then we will finish the proof today. Okay, that's all that we will do today. I'll make one or two remarks, which are also remarks from Rudin. So this was the starting point. We considered the collection of all injective holomorphic mappings from omega to U. So what was omega? Omega is any simply connected region which is not the whole of C. So we considered the collection of all holomorphic mappings into U, injective on omega, injective in omega, and our first claim was to prove that this is non-empty. Right? We wanted to show that there is a psi here which is also onto. That was the claim. That's what we wanted to prove. But first of all, we showed that this is non-empty. And how did we show that this is non-empty? By first considering Z minus W naught. So you take a W naught in C minus omega. Omega is not the whole of C. So there is such a point. And then consider the function Z minus W naught. So this is non-vanishing throughout omega. Therefore, it has a holomorphic square root, which we call phi. So phi is a holomorphic square root of this function. So we considered this function and then we adjusted it by R by phi plus A. We considered what is R and A? We considered a disk with center at A and radius R completely contained inside phi of omega, and such that d minus a r and dar will not overlap. And if you choose any such r and that kind of a, and if you take this has the property that psi maps into u, and psi is 1 1 because this phi is 1 1. So psi is holomorphic because this is well defined. Phi plus a is never vanishing. So psi is a holomorphic function injective in omega into u. So we have exhibited such a psi by considering a holomorphic square root. So sigma is non-empty. Here DAR is contained in phi omega and any R less than mod A would work. So this was the first claim. Okay. And the second claim was that you can increase the speed. If psi is a function which is not on 2, then you give me a z0 and I can find a psi1 whose speed at z0 is higher than the speed of psi at z0. So there exists a psi1 in sigma such that modulus of psi1 prime at z0 is bigger than, strictly bigger than mod psi prime at z0. This used Schwarz lemma ideas. So we use the extremal problem of Schwarz's lemma and also Schwarz's lemma. So let's quickly recall the proof, and we took the holomorphic square root again. So what we did is you took an alpha in U outside psi of omega. Why is this possible? Because psi is not onto. Psi is not onto U. Therefore, there is an element in U which is outside psi omega. And then we considered phi alpha. So what is phi alpha? This is a function z minus alpha by 1 minus alpha bar z. And these are nice functions because alpha belongs to U. So these are automorphisms of U. So psi is from omega to U and phi alpha is from U to U. So this composition is from omega to U. And because phi alpha is an automorphism, it's a bijection, psi is 1 1. So the composition of 1 to 1 functions is 1 to 1. So this is 1 to 1. And we extracted a holomorphic square root, and this g is also 1 to 1 because this is 1 to 1. And this is never vanishing. This is never vanishing. That's why you took you could take a holomorphic square root, and this is never vanishing because phi alpha vanishes only at alpha, and psi is never alpha. Psi is never alpha. So this is non-vanishing. We took a holomorphic square root, and that is also non-vanishing. That is also 1 1. And then we took gz0 to be beta, right? Z0 is given to you, and you have extracted this g, you evaluated z0 and call it beta and considered this function. What is this s? Symbol s denotes what? Can someone recall? This from the last class. Yeah, what is s? You said it maybe, but I couldn't hear.
The square function.
Square function. Yeah, s is just squaring. S of z is z square. So you took phi minus beta, then composed with s, then composed with phi minus alpha, and then we concluded. Sorry, tell me again. Somebody was going to speak now. Maybe not. So we proved this. How did we prove this? We proved this by looking at, right, that extremal thing we use. That extremal thing we use for the point 0 and the image, right? Whenever you had f of a is b, you could evaluate f prime a. And mod f prime a is less than or equal to 1 minus mod beta b square by 1 minus mod a square. So you are taking a to be 0 and b to be f of 0. So f prime at, and f is this function. So f prime at 0 will be less than 1 minus mod f of 0 square by 1 minus 0 square. So that is less than or equal to 1 minus mod f of 0 square. And then we claim that f of 0 cannot be 0, and therefore it is strictly less than 1. What happens if f of 0 is 0? Then it would have been equal to 1. But if this is equal to 1, then Schwarz's lemma would say that f is a rotation. F is a scalar multiple of the identity, and with modulus of the scalar is 1, so it's a rotation, and that would be 1 1. But this f is not 1 1 because squaring is involved, and that shows that less than or equal to 1 is in fact strictly less than 1. That's how we got strict inequality here. So this was important. Getting the strict inequality was important. So via the extremal problem you got less than or equal to 1, and via the Schwarz's lemma you got the less than or equal to be strictly less than, and that was important. And then what did you do? Then you did the chain rule. So you take psi1 to be phi beta composed G, and if you take psi1 to be phi beta composed G, now you can see what is the relationship between psi and psi1. So if you apply phi minus beta to psi1, phi minus beta, I can highlight phi minus beta if you apply to psi1. So put composed with psi1 here. What will you get? Phi minus beta composed with psi1 is G. And then you are squaring G. So you got G square, which is phi alpha composed with psi. And then if you apply a minus phi minus alpha, which is the inverse of phi alpha, what you get is psi. Okay, so you see that psi equal to f composed with psi1. This composed with psi1 is psi. So psi is f composed with psi1. Apply chain rule. So if you apply chain rule, psi prime at z0 will be f prime at psi1 z0. But what is psi1 z0? Psi1 at z0 is phi beta of g z0, but g z0 is beta. So it is phi beta at beta, which is 0. So when you apply chain rule, psi prime at z0 is f prime at 0 times psi1 prime at z0. F prime at 0 times psi1 prime at z0. F prime 0 modulus is strictly less than 1. Therefore, modulus of psi prime at z0 is strictly less than modulus of psi1 prime at z0. So that finishes this proof. So this is the second claim that we did, that whenever you have a point, whenever your function is not onto given any point, I can increase the speed there by I can get another function whose speed there is strictly bigger. And therefore, in order to show that there is an onto function, you just have to show that if you take the supremum of all the speeds at z0, and if you can get a function h which attains that supremum, h prime at z0 modulus is equal to this supremum, then that h has to be onto. Is that clear? If you take supremum of mod psi prime z0 as xi varies over sigma, and if you can show a function h such that modulus of h prime z0 equal to that supremum, the highest speed is attained at z0, then that h has to be onto. Why? Because if h is not onto, you can get some other function whose modulus, the speed there is even bigger, but this is already the supremum, the highest is attained, so you cannot get a higher one. Therefore, it has to be onto because of this claim. Okay, so we continue with the proof. Sigma is a normal family. Why is sigma normal? Because Montel's theorem says that if you have locally uniformly bounded on any compact set, if you have uniform boundedness, then a family of holomorphic functions will be normal. And sigma consists of functions which are valued in U. So you have uniform boundedness throughout. You have global uniform boundedness, much more than what is required in Montel. Therefore, by Montel's theorem, it's a normal family. And so this implies, so this is one thing which I did not stress much, but I did not stress much because I'm not very sure whether this fact is required for us, but I don't see another proof. So let me just state it that normal means what? Given any sequence, it has a subsequence that converges. The limit need not be part of sigma, but if you take sigma closure, the bar, where are you taking bar? In the space of all continuous functions. And this can be made to be a metric space. You can put a nice metric, and then it's a complete metric space. If you are interested, you can refer Conway. Conway explains all these things. And then sigma bar is sequentially compact, and you are in a metric space, therefore it is compact. Okay, so normality is very much related to compactness of its closure. Bar is compact, and therefore the supremum exists, right? supremum psi prime z naught, psi in sigma bar exists and therefore psi in sigma exists. Because psi going to modulus of psi prime z naught is a continuous function under this topology coming from this metric. So this exists, the supremum exists, and we need to show that there exists an h in sigma such that modulus of h prime z naught is eta. The highest speed is attained by an h. Once we show that, is it clear to all of you that h has to be on 2? Because if h is not on 2, I can find an h1 such that modulus of h1 prime at z0 is strictly bigger than this. But you can't find something which is strictly bigger than this because this is already the supremum as psi varies over sigma. And therefore this h has to be on 2, and that's what we need to show. So proof is easy. Give me a second, I mean 1 minute. I'm taking a 1 minute break. I'll just come back. So let me just
Here are we saying that eta exists because sigma closure was compact?
so you can hear me, right? I have unmuted, and yeah, so let's continue. So there exists a sequence. Yeah, so again, I'm going to use normality in the very next line, but because it is the supremum, eta is the supremum of all these things. So there exists a sequence psi n in sigma such that modulus of psi n prime at z naught converges to eta, right? Because eta is the supremum, so you can get a sequence here. This is psi over sigma, so you can get a sequence psi n in sigma such that modulus of psi n prime at z naught converges to this number eta. But remember, it's a normal family, so any sequence has a subsequence that converges uniformly on compact subsets because of normality. There is a subsequence that converges uniformly on compact subsets. Without loss of generality, we will denote it by the subsequence again by psi n, right? I mean, this is abuse of notation. The subsequence let us denote again by psi n, and therefore you have got eta equal to limit mod psi n prime z naught. No, that anyway you had. And you have got a subsequence which converges. So let's denote the subsequence is denoted again by psi n, and then what we have got is, let's call the limit to be h. H is limit psi n, and I'm going to show that this h is onto. Okay, but h is holomorphic, right? Why is h holomorphic? Why is h holomorphic?
Because the convergence is uniform on compact subsets.
Convergence is uniform on compact sets, therefore the limit is holomorphic. And what can you say about h prime at z naught modulus? H prime,
it is eta.
It is equal to eta because psi n converges to h, therefore psi n prime converges to h prime, and therefore psi n prime at z naught converges to h prime at z naught. Psi n prime at z naught converges to h prime at z naught. Therefore, modulus of psi n prime at z naught converges to h prime at z naught modulus, which is eta. Therefore, by the compact convergence result, h is holomorphic, and moreover, h prime is limit psi n prime, and therefore modulus of h prime at z naught is eta. So So you have got a function. You've got a function h in sigma. No. Have I shown that h is in sigma? I haven't shown that yet. What is sigma? Sigma is all holomorphic functions on omega valued in u and injective in sigma, injective in omega. What I have shown is this property is true. I have got a holomorphic function in omega such that this property is true. But I have not shown that it is valued in u. I have not shown that it is injective. So I'm going to show now that h is valued in u and also h is holomorphic, I already know. And this property is proved. Now I will show that h is valued in u and h is injective. And therefore you have got an h in sigma such that this is true and therefore that h has to be onto, and that will finish the proof. Right? You just needed an onto function in sigma. So we are going to show that this h belongs to sigma. So first of all, sigma is non-empty. This is what we proved at the starting. And because sigma is non-empty, what can you say? You can say that this eta is a positive quantity. Right? Sigma is non-empty set. So there is at least one psi here. And therefore psi prime at z0 is non-zero. Why is psi prime at z0 non-zero if psi is a function here? I claim that psi prime at z0 is non-zero.
Because it's injective.
Because it's injective. Therefore, this is non-zero. Therefore, supremum is non-zero. Because this is non-empty, this eta is positive. So, because eta is positive, what can you say about h? Because eta is positive, h prime at z0 is non-zero. Therefore, h is not a constant function. Right? If h was constant, h prime would have been zero everywhere. So first of all, we conclude that h is not a constant function. This is because this is non-empty. It is not a constant. Now I'm going to conclude that it is valued in u. That's easy because each of the psi n is from sigma. So psi n of omega is contained in u for each n. So when you take limit, what will happen? H is nothing but the limit of psi n. So what can you conclude about h of omega?
That it will be in the closure.
It will be in the closure of u for sure. H omega is contained in u bar. And therefore, I conclude that h omega is contained in u. Why?
OMT.
OMT. It's holomorphic. So if it's contained in u bar, it's contained in u by open mapping theorem. So we have proved that it's valued in u by once again appealing to the open mapping theorem. Earlier, we appealed to open mapping theorem in the very first claim. When sigma is non-empty, we had used open mapping theorem. Okay, so this is one part. Now what do we need to show? We need to show that h is injective. Okay, so that is Rouché's theorem. So we need to show that h is injective. So let z1 not equal to z2 in omega. We need to show that h of z1 not equal to h of z2. Okay, so let's name psi n at z1 and h at z1 we will consider. So z1 not equal to z2 are any 2 points. At z1 you take psi n of z1. Let me call it alpha n, and h at z1 let me call alpha, and take a closed disk with center at the other point z2. So take a closed disk inside omega with center at z2, and with a further property. So take this disk small enough so that z1 is not part of it, right? So z1 and z2 are two distinct points. So you can take a small disk around z2 so that z1 is not part of it. This is obvious. You can also take it the disk small enough so that h minus alpha has no zero on the boundary of d bar. Why is that? Because if h minus alpha has a zero on the boundary of every closed disk, right? You want to take a closed disk so that on the boundary h minus alpha has no zero. If that you can't do, that means whatever closed disk you take centered at z2, h minus alpha has a zero on the boundary. That will show that the zeros of h minus alpha has a limit point, which is z2. But zeros of holomorphic functions cannot have a limit point. So therefore, there is a d bar such that h minus alpha has no zero on the boundary of d bar. right? Otherwise, any small disk you take on the boundary, there is a 0. That will make Z2 a limit point of the zeros, because all these disks are centered at Z2. So you can do this. So H minus alpha has no 0 on the boundary of D bar. And note that the function psi n minus alpha n, psi n converges to H, right? H is the limit of psi n. So psi n minus alpha n, and alpha n converges to alpha, because psi n z1 converges to the limit, right? At the point wise, alpha n converges to alpha. So psi n minus alpha n converge to psi minus alpha uniformly on D bar, because all the convergence is compact convergence. So D bar is compact, it's a closed disk, bounded closed disk. So D bar is compact, therefore convergence is uniform. So psi n minus alpha n converge to psi minus alpha uniformly on D bar.
I think that is H minus alpha. Psi n converges to H.
You are right, there is no psi. Yeah. Who's this speaking? Who's this? Is it Onkar who just spoke?
Surya Pratap.
Surya Pratap. Okay, thanks Surya Pratap. Yeah. I should change it to H minus alpha, because psi n converges to H. So psi n minus alpha n converge to H minus alpha uniformly on D bar. Okay. Now Rouché's theorem, what does Rouché's theorem say? If f and g are two functions such that mod of f minus g is strictly less than, you can take mod f plus mod g or one of those, mod f maybe, then f and g have the same strictly less. If you have the strictly less inequality on the boundary, right? On a curve gamma, then in the interior of gamma, interior quote unquote, in terms of the index, the interior f and g will have the same number of zeros, right? And as a corollary, you can prove that if fn's are functions which converge to f, if fn converges to f, and if fn's have, and if f has no 0 on the boundary, then fn and fn's and f will have the same number of zeros in D, right? Because if fn converges to f on D bar, modulus of fn minus f can be made uniformly, it can be made small, less than some epsilon. So it is less than, so it can be made to be less than mod fn plus mod f on the boundary, right? Therefore, fn and f will have the same number of zeros. So this is Rouché's theorem, and we are going to apply that. So note that fn psi n minus alpha n have no 0 in D. Why is that? Psi n minus alpha n, these functions have no 0 in D, because psi n minus alpha n have a 0 at Z1, but Z1 is outside D. So Z1 is a 0 and Z1 is outside D, and these functions are 1, 1 functions, so they cannot have more than one 0. Right, psi n is 1, 1, therefore psi n minus alpha n is 1, 1, and Z1 is a 0, so it cannot have any other 0, and Z1 is outside D, therefore there is no 0 in D. Since they are 1 to 1 in omega, they have no 0. Therefore, the conclusion is that h minus alpha, the limit h minus alpha has no 0 in D by Rouché's theorem. By Rouchet, h minus alpha has no 0 in D, and in particular, h of Z2 is not h of Z1. Because h minus alpha has a 0 at Z1. And h minus alpha cannot have a 0 in D. In particular, h minus alpha cannot have a 0 in Z2, and therefore h of Z2 cannot be alpha, but h of Z1 is alpha, so h of Z2 is not h of Z1. So by Rouché's theorem, it follows that h is injective. If Z1 is not equal to Z2, then h of Z1 is not equal to h of Z2. So this finishes the proof of Riemann mapping theorem. Any question on the proof? We have time, so we can quickly discuss.
Did we use Rouchet on in the last case?
Say that again.
On what functions did we use Rouchet?
Yeah, so I think what we are doing is, suppose you have a sequence of functions fn, and suppose it converges to f. Okay, and suppose f has no 0 on the boundary. Suppose you are on some omega, and on omega bar f has no 0. Then we want to say that fn's and f have the same number of zeros inside omega.
Okay.
And this follows by Rouchet, right? Because fn converges uniformly to f. So modulus of fn minus f is very small. So you can, get that strict inequality on the boundary. There's a
Okay,
small
fine.
check to be
Okay,
done.
got it.
Yeah, there's a small check to be done, which I haven't checked, but you can check. Because fn minus f is small enough. So you can, maintain the strict inequality. So you're also using f as no 0 on the boundary. Why are you using that? In order to
Because then
Yeah,
that is strictly
otherwise,
positive.
fn minus f, and if f is 0, then mod fn minus f is mod fn. So you will not get a strict inequality. So because f has no 0 on the boundary, you are getting a strict inequality. You are getting a strict inequality for some fn, right? Because
Yeah,
if it vanishes on the boundary, then you are not getting a strict inequality. But
yeah.
because fn converges to f and f has no 0 on the boundary, there is at least one fn which has no 0 on the boundary. In fact, there are many fn's with no 0 on the boundary. And for those fn's, Rouchet's theorem will apply. And fn,
Or I think just because f has no 0 on the boundary,
yeah,
mod f on the boundary, the infimum is positive.
correct.
And then we can choose n large enough so that fn minus
Correct.
f, the mod is less
Correct.
than that on the boundary.
So
Yeah.
there may be some fn's which vanish on the boundary, but we will not consider those. Right?
Yeah, yeah.
So we only need, one fn and f to have the same number of 0. That's all that we need. Therefore, fn's and one fn and f will have the same number of 0, but no fn has a 0 in D. Therefore, f has a no 0 in D by Rouchet. Is that clear?
Yeah.
Okay. Any other question? Anyone else? Okay. So what have we done? We have taken a simply connected domain, simply connected region, and it is not the whole of C. Then we constructed some, at two places we use the fact that holomorphic, non-vanishing holomorphic functions admit a holomorphic square root. And that's the only property of simple connectedness that we have used. There's no other property of simple connectedness that we have used. So if you have a region where holomorphic functions admit, non-vanishing holomorphic functions admit holomorphic square roots, then we have shown that such a region is bioholomorphic to U and hence simply connected. So we have also proved that equivalent characterizations, whatever was remaining, we have proved that. And what was the strategy here? We considered all injective holomorphic functions valued in U, and we showed that there is at least one which is onto. And inverse being holomorphic is automatic because injectivity gives you derivative is non-zero, and then inverse function theorem applies locally everywhere. So inverse is holomorphic everywhere, locally everywhere, and therefore everywhere. So inverse holomorphic we need not show. I mean, it's automatic. So this is what we have done, but the next two remarks show that there is something more which we have done. So let us go through that. Okay. The first remark is, so this is 14.9 remark in Rudin. There are two remarks. First remark is that we can conclude that H, so H is our biholomorphic map, right? H from omega to U is injective and onto, and we used only one point. It was very powerful. Montel's theorem is so powerful that given one point Z0, we use that Z0 and the speed there in order that H is onto injective and valued in U. The attaining supremum, maximum speed at one point was enough. That particular point, H of Z0 is not any point in U, it is actually 0. We don't need this in the proof, but this is an extra observation. Why is that? H of Z. So the picture to keep in mind is something like, upper half plane to the open unit disk Z minus I by Z plus I. So I goes to 0, that kind of a thing. So whatever point Z0 you choose, the proof of Riemann mapping theorem that we have done, the H that it constructs it quote unquote, because it's using normal family, so it's not a construction showing the existence. So quote unquote constructs that H has the property that it takes this point Z0, the distinguished point Z0, where the speed is maximized. It is going to the origin of the disk, the center of the disk. Why is that? Because otherwise, suppose not, then Hz0 is some beta which is non-zero, and in which case you do the following. You compose H with further with a phi beta. This is also in sigma. This kind of arguments we have done many times. Take its prime derivative at Z0. So by chain rule, this will be phi beta prime at Hz0. Hz0 is beta. So phi beta prime at beta times H prime Z0. But phi beta has a formula. Therefore, phi beta prime at beta you can evaluate, and we have done this long back. This is nothing but 1 by 1 minus mod beta square. It is actually equal to 1 by 1 minus mod beta square. Therefore, this is equal to mod H prime Z0 by 1 minus mod beta square. But if beta is not 0, then what happens? If beta is not 0, then this is strictly less than 1. Denominator is strictly less than 1. Therefore, the whole thing is strictly bigger than mod H prime Z0. But this cannot happen, right? There cannot be anything in sigma, because the H that we have constructed has the property that the maximum speed is attained at Z0. Therefore, this cannot happen. The contradiction is because beta is non-zero. So beta is 0. Then there's no contradiction. If beta is 0, then it's an equality. So this is automatic. So the proof is so good. This, the proof is maximizing the speed at a point that you have given me. You give me a point, I will construct a function, quote unquote, construct a function whose speed is maximized at that Z0. And then one corollary to the proof is that Z0 is mapped to the origin. So it's very nice. And the second remark is, if f is any function omega to u holomorphic, need not be 1 to 1. Right? What are you maximizing? The maximizing h that you have taken, the speed maximization you have taken over sigma. Sigma consisted of 1-to-1 functions in omega valued in u. But the next remark says that even if you don't take 1-1 function, still h is the maximum speed. Say the construction of h was such that it attains a maximum speed over all injective functions valued in u. But we are going to show that even if you take a non-injective function valued in u holomorphic, the speed is still maximum for h only. H has higher speed. So even if it's not 1-1, doesn't matter. You consider the function f composed h inverse. This is fine, no? Because h is bijection, therefore h inverse makes sense. And composed with f, you have got some other holomorphic function. I'm not assuming 1-1ness for this. And this maps u to u, no? Because h inverse maps u to omega. H is from omega to u bijection. So h inverse maps u to omega, and f maps omega to u. So this maps u to u. And what is modulus of g prime 0? Modulus of g prime 0. So do chain rule. So what is g prime 0? G prime 0 will be f prime of h inverse 0. But what is h inverse 0? H inverse 0 is Z0. So it will be f prime at Z0 times h inverse prime at 0. But h inverse prime at 0 is what? H inverse prime at 0 is 1 by h prime 0. Right? Inverse has this nice property. So h inverse prime at 0 is 1 by h prime 0. So g prime at 0 is, no, g prime at z.
Will it be 1 by h prime Z0?
1 by h prime Z0, correct. So g prime at 0 is f composed. No, so f prime at h inverse 0, which is Z0, times h inverse prime at 0, but h inverse prime at 0 is 1 by h prime at Z0. You are right. Right, the 0 and Z0 are mapped to each other. So it is 1 by h prime at Z0. So what you are getting is f prime at Z0 by h prime at Z0. This, how did you get? Mod G prime 0 is less than or equal to 1 by Schwarz's lemma, because G is mapping U to U and G is holomorphic. Therefore, mod G prime 0 is less than or equal to 1. This is by Schwarz's lemma. So I jumped the gun. I was going to the next argument. So this is by Schwarz's lemma with equality if and only if G is a scalar multiple of the identity with modulus of the scalar is 1. If and only if G is a rotation. Now apply chain rule. By chain rule, G prime at 0 is f prime z naught by h prime z naught. So mod G prime 0 less than or equal to 1 tells you that mod f prime z naught is less than or equal to mod G prime z naught with equality if and only if f of z is lambda times h of z for lambda in S1. So what is the point of this particular remark? This remark tells you that even if you don't assume f to be 1, 1, even if you don't assume f to be 1, 1, f is any holomorphic functions valued in on omega valued in u, then you are showing that modulus of f prime z naught is less than or equal to modulus of h prime z naught. So the h that you have constructed in the proof of Riemann mapping theorem, which maximizes the speed at z naught over all injective holomorphic functions valued in U, is automatically maximizing over all holomorphic functions valued in U. What is maximizing speed over injective holomorphic functions is in fact maximizing speed over all holomorphic functions. Injectivity is not required in order for this to be bigger. Okay, so the proof has much more in it. One is it takes the distinguished point z0 to the distinguished point, right? Any disk has a distinguished point, which is the center of the disk. So the point where we maximize speed is going to the center of the disk 0, and it is automatically maximizing over all holomorphic functions. So it's very beautiful. Okay, so that's all that we have for the lecture part. So let me stop here. Let me stop sharing the screen, and I will also download the attendance. Okay, all right. So I will stop this recording and start the new recording.